Hello dear students, welcome to our online learning process. Myself Mrs. Vanita Gaikwad from HPT Arts and RYK Science Junior College, Nasik. Let us continue with our second lecture of magnetic fields due to an electric current. Let us consider the magnetic force on a wire carrying a current. First of all, let us consider a straight wire. As shown in the figure, consider a wire of length L. An external magnetic field B bar is applied perpendicular to the wire coming out of the plane of the paper. Let I be the current flowing through the wire under an application of potential difference. If Vd is the drift velocity of conduction of electrons in the part of length L, the charge Q flowing across the plane in time t will be Q equal to IT. Substituting time equal to length upon drift velocity, we can write Q equal to IL upon Vd. Let us call this as equation number 1. As the magnetic field is perpendicular to the current carrying wire, the magnetic force Fm bar will act on the charge. It is given by Fm bar equal to Q into vector product of Vd bar and B bar. By the definition of vector product, this equation can be written as ILB dot Vd sin theta n cap upon Vd. Therefore, Fm bar equal to ILB sin 90 degree n cap. 90 degree is the angle between L bar and B bar, where n cap is a unit vector perpendicular to both magnetic field and drift velocity in the direction of Fm bar. Therefore, the magnetic force Fm bar is equal to ILB n cap. This is the magnetic force acting on the portion of the straight wire having length L. If the field is not perpendicular to the wire, then the above equation takes the form Fm bar equal to I into L bar cross B bar. Let us consider the magnetic force for a different shape. Consider an arbitrarily shaped wire. Then this equation can be extended to a wire of arbitrary shape. Let us consider a segment of infinitesimal length dl along the wire. If I is the current flowing through this part of the wire and magnetic force due to perpendicular magnetic field B bar is given by dF bar m equal to I dl bar cross B bar. See here we are considering a small part of length dl bar. So for this part we will also consider the small force df bar. The total force on the total length of the wire is given by Fm bar equal to integration of df bar. Here integration of df bar means the addition of all small elements of length dl bar. It is equal to I integration dl bar cross B bar. If B bar is uniform over the whole wire, it can be written as Fm bar equal to I integration dl bar cross B bar. Now let us consider the force acting on a closed circuit in a magnetic field B bar. From the same equation extended to a closed wire, we can write Fm bar equal to closed integral I dl bar cross B bar. For the closed loop or for the closed wire circuit, the sign is a small circle marked on the integration sign with letter C at its base. Here the integral is over the closed circuit C. So for uniform magnetic induction B bar, the equation can be written as Fm bar equal to I closed integral over dl bar cross B bar. The term in the bracket is the sum of vectors along a closed circuit. Hence, it must be 0. Therefore, F bar equal to 0. To study the torque acting on a current loop, let us refer the working principle of an electric motor. That is, the magnetic force acts on a current carrying wire due to a magnetic field. Figure shows the current carrying wire loop of rectangular shape is placed in the uniform magnetic field produced by the two strong magnets. The segment AB and CD of the loop are perpendicular to the direction of magnetic field B bar. Therefore, the magnetic force Fm bar will act on the sides AB and CD in opposite directions. The direction of this magnetic force Fm bar can be given by Fleming's right hand rule. The rule is explained as let the pointing finger of the right hand show direction of current, the middle finger shows the direction of magnetic field B bar, then the stretched thumb indicates the direction of. Explain the action of rotation of the loop due to the torque. Let us consider the figure showing rectangular loop ABCD placed in a uniform magnetic field B bar with sides AB and CD perpendicular to the direction of magnetic field, but sides BC and AD are not perpendicular. Due to the magnetic field B bar, forces will be exerted on each side of the loop. The force F4 bar on side BC will be given by the equation F4 bar equal to I L2B sine of 90 minus theta, because the side BC is not perpendicular to the direction of magnetic field. The angle between the side and magnetic field is 90 minus theta. Similarly, the force F2 acting on side AD is equal and opposite to F4 bar. They will cancel out each other. The magnitudes of forces F1 bar and F3 bar on the sides AB and CD will be I L1B sine 90 degree. These two forces do not act along the same line, hence they produce a net torque. The axis of rotation passes through the centers of sides AB and BC of length L2. So by the definition of moment R, it is half L2 sine theta. The torque tau due to forces F1 bar and F3 bar will then be torque equal to I L1B half L2 sine theta plus I L1B half L2 sine theta. So here the addition of these two torques is I L1 L2 B sine theta. So the net torque acting on this loop is I L1 L2 B sine theta. If the current carrying loop is made up of multiple turns N in the form of a flat coil, the total torque will be N into tau. Therefore, we can write tau dash equal to N I L1 L2 B sine theta. Let us substitute the term A for L1 and L2. So the equation becomes tau dash equal to NIA B sine theta. Here A is the area enclosed by the coil, and this equation holds good for all flat coils irrespective of their shape in the uniform magnetic field. Our next article is moving coil galvanometer. The galvanometer is a sensitive electromagnetic device which is used for detecting and indicating electric current. It can also measure low currents even of the order of few microamperes as we used in our labs. Its working principle is like this. When a coil carrying an electric current is suspended in an uniform magnetic field, a torque acts on it. This torque tends to rotate the coil about the axis of suspension so that the magnetic flux passing through the coil is maximum. In other words, the current in the circuit can be measured in terms of a torque exerted by a magnetic field on a current carrying coil. Let us discuss its construction. Moving coil galvanometer consists of a thin insulated copper wire with several turns wound on a non-magnetic frame of aluminum or copper. The coil is suspended in such a way that it can freely rotate about an axis in the uniform magnetic field set up between two strong poles of horseshoe magnet. A soft iron cylindrical core makes the field radial and as the current flows through the coil, it rotates due to a torque acting on it. This torque is given by the equation τ equal to NIAB. Here, A is area of the coil, B is the strength of magnetic field, N the number of turns of the coil, I is the current in the coil. Sin theta equal to 1 as the field is radial. This magnetic torque is balanced by a counter torque due to a spring so that a fixed steady current I in the coil produces a steady angular deflection phi. Larger the current, larger is the deflection, and larger is the torque due to the spring. If the deflection is phi, the restoring torque due to the spring is equal to K phi, where K is the torsional constant of the spring. Here the restoring torque is K phi. So equating both the values of torque, we can write K phi equal to NIAB. Rearranging the terms in the equation, phi equal to NAB upon K into I. Thus, the deflection phi is proportional to the current I flowing through the coil because remaining parameters in the equation are. In the chapter electrostatics, you have studied electric dipole moment. Similarly, in this chapter, the analogous term magnetic dipole moment is explained. Mu bar is magnetic dipole moment of a current carrying coil. Magnitude of magnetic dipole moment mu is equal to NIA. Product of number of turns, current passing through the coil and area enclosed by each turn of the coil. The torque which causes the rotation of the coil in uniform magnetic field B bar will be represented by the equation τ equal to mu b sin theta. Theta is the angle between mu bar and B bar. Therefore, we can write the vector form of above equation as tau bar equal to mu bar cross B bar. Torque on an electric dipole exerted by an electric field E bar is given by tau bar equal to P bar cross E bar. These two equations are analogous to each other. Similarly, the term magnetic potential energy of a dipole is analogous to electric potential energy of an electric dipole. Electric potential energy is associated with an electric dipole due to its orientation in an electric field. The potential energy capital U of an electric dipole P bar in an electric field E bar is given by the equation U equal to minus P bar dot E bar. Analogously, the magnetic potential energy of a magnetic dipole mu bar in a magnetic field is given by U equal to minus mu bar dot B bar equal to minus mu B cos theta, where theta is the angle between mu bar and B bar. Now here we will consider two cases, if theta equal to 0 and if theta equal to 180 degree. If theta equal to 0, U equal to minus mu B, the minimum potential energy of the magnetic dipole in a magnetic field when mu and B are parallel to each other. And if angle theta equal to 180 degree, then U equal to mu B, the maximum potential energy of a magnetic dipole when the magnetic dipole moment and magnetic field are antiparallel to